Hello, everyone. We are Team Cambridge. Welcome again to our symposium. Our project is ScanHead System Controller with Polygon ScanHead integration. I'm Nick Schmidt, studying electrical engineering. There's my partner Rory, electrical also, and Travis Frink, electrical and computer. So to begin, our company, Cambridge Technology, among a few other things, produces this system right here, which is a laser scanning head, a controller, and a software package. That stuff, among a few other things, does laser etching, which you can see on the right. So your MacBook keys, numbers in products, QR codes, and the funny little iPod engravings that they used to do. So basically, what the project is Cambridge produces this. All three of those things are produced by Cambridge Technology. What we were presented with is they acquired a company that makes this, which is a completely different technology, which I'll explain in a second. Currently, they use a competitor's controller and a competitor's software, which is just a big no-no. So basically our target is to get that ScanHead integrated with Cambridge Technology's products so that everything works. So I'm going to go over a little bit of the technology behind the two different scanning systems. This is the Galvo-based one, which is what's currently supported by Cambridge's product. It involves two Galvos, which are basically motors with mirrors attached to them. And this is optimized for vector scanning, so the laser turns on, like this right here, and the motors move and it moves the laser. Whereas this system, which is the target system, is a polygon ScanHead based system, which you can see the continuously rotating polygon, which acts as one of those Galvos and has just one Galvo that only has to move once per line. Raster images are produced pixel by pixel, as you can see right here. So you can see the difference right there. So our anticipated best outcome, as I was speaking, are basically to take the acquired ScanHead with the competitor's controller and make it work with Cambridge Technology's product. And this is difficult and it's going to be challenging because of how efficient and how exact the actual laser has to be, like microns. It's really, really tiny. Some of the project implications are that the customers may be familiar with the ScanMaster controller environment, and they will be more likely to upgrade to the newly acquired product if they're familiar with the environment. It'll also stop giving business to one of the main competitors, which is always an improvement, and will generate maybe about $500,000 to $1 million in annual income. So quickly, before I hand it off about our key accomplishments, here's kind of how the system works. You have a PC on the user side running the software ScanMaster Designer, which sends jobs to the Zinc framework, which is basically the controller itself, which is kind of where all the magic happens, where all the calculations happen, all the outputs are generated, which go to the two hardware pieces, the laser control and the ScanHead itself.
Thank you. So we began this semester with a general footprint for our project using the previous Cambridge Technologies technology. First is a user computer here with ScanMaster Designer. ScanMaster Designer being Cambridge Technologies' user interface for creating laser jobs. This is their meat and bone that their customers are really used to. It's kind of a great starting point. It's very adaptable and easy to use. It is connected to an Ethernet connection and a JTAG connector for our debugging purposes to the ScanMaster controller. The ScanMaster controller is that Zinc architecture that Nick previously talked about. It is the brains of the technology. It does the calculations. It receives these jobs and processes it into, first the power to the Galvos, and then the Galvo ScanHead. We are going to adapt this model into our Polygon model by removing certain parts and adding in the Polygon. So first we began by creating a testing environment. We used TCP and IP connection, this Ethernet cable, and a serial connection, this JTAG connector, in order to debug the previous software. We walked through line by line to figure out the exact operations of the previous architecture in order to adapt it into our future model. Using the Xilinx software development kit and the Vivado design suite, we probed the model and started generating new models for our software. So going through the software, we became really familiar with the architecture, including a Linux server based on board and one of the processors aboard the Zinc architecture that takes user input and translate it into machine code for the bare metal processing on a second processor on the Zinc architecture. This then chops it up into a package that's more readable translates it over to the Verilog logic, which then outputs it into the laser and the motor controls. One of the most observable accomplishments of our work so far has been the data compression within the SMC. Before, it used a 0 to 255 value that would denote the length or darkness of a pixel. We changed that to a 0 or 1 value. And the reason we did this was that it saved a lot of memory inside of the SMC, which allowed it to process the data a lot faster and keep up with the polygon and actually output the pixels in a way that lined up one next to each other to form a perfect grid. And now I'm going to hand it off to my teammate Travis for our future technical accomplishments.
So moving forward with our future challenges, in order to incorporate ScanHead-specific functionality into the SMC, we need a way to interface with the ScanHead itself and its control signals. Currently, the ScanHead is only capable of interfacing with the competitor's controller, so we recently acquired this breakout board to enable us to interface with it. Eventually, we'd like to make a custom PCB which would allow us to have a more robust solution to this problem. Once we can interface with these control signals, we can move to polygon ScanHead integration. Now, starting with these three first main points, these are what are essentially needed for basic ScanHead functionality, or basic raster functionality. So starting with polygon speed control, this will be done first because it is the easiest change that we can make to the system, and also will allow us to make the next change, which is laser timing control, where we will use the signals from the ScanHead to properly time the laser output to sync with each facet of the polygon. Lastly, we'll move to Y galvo control. This will allow us to scan in the direction perpendicular to the scan of the polygon and allow full raster scanning capability. Once we have that, we can move to adding features which will allow higher quality raster scanning, such as lens correction and polygon facet correction. Once we have raster scan capability, we can move to add features which will allow the user to configure the polygon scanner to their needs. So using Cambridge Technologies Scan Master Designer, users can configure things, and jobs are generated using Cambridge Technologies ScanScript language. If we add custom functions to this language, we can allow the user to configure the polygon to their specific needs. And with the addition of that feature, we will have finished our anticipated best outcome. We'd like to thank Professor Sunak as well as our technical directors for their help on the project. If you'd like, you can see the systems in action at our demo after the presentation's over. Thank you.